Good morning, everyone. Welcome to our session. My name is Gaurav Saxena. Our topic is around Ursa, augment your lakehouse with Kafka-compatible data streaming capabilities. I'm delighted to introduce my co-speaker, CJ Go. He is also one of the original creators of Apache Pulsar. Go with the quick agenda. I'm going to start with outlining the enterprise needs that we face in handling high volume real-time data. Then I'll hand it over to CJ, who will explain how Ursa Engine paired with Apache Iceberg can directly address the challenges that we're going to talk about in the first 2 points on the slide deck. So enterprises, they deal with massive data streams from data coming from the IoT sensors in connected vehicles to the user log data. Now, in this environment, we can't wait for hours or days for insights. We need real-time processing. However, moving real-time often adds complexity. Traditionally, batch-oriented ETL pipelines might have been fine at a smaller scales, but they simply break down under high volumes and velocity that we see. When you're operating at the scale of Fortune 500 companies, I'm from an automotive industry, so I'm going to speak from the experience in the connected vehicle world. These are the 4 areas are very critical, right? So you have regulatory requirements that demand strong governance, specifically for safety and privacy. And then you have the spiral costs, because if you're moving the same data back and forth between one streaming platform to the streaming platform, your costs has become exponential. And then as far as scalability, a single software update across millions of vehicles can generate a massive spike of telemetry in the data, and so your platform should be able to handle that load. And finally, open standards and interoperability are for our long-term investments. They allow us to pivot as new technologies emerge. To put things in perspective, consider the connected vehicle program. There is a statistics that within this decade, there will be 100 millions of vehicles talking to the connected platform. If you own Tesla or any of the recently built vehicles, you want your vehicles to be performed better daily. The over-the-air updates, you want the fleet and prognosis of the data from vehicles to your cloud platform. You can't have a place where you can say you're keeping the maintenance window, because the software, the vehicle is basically nowadays software-defined vehicles. Right, so traditionally, how you handle that is basically you have a large amount of Kafka clusters to manage ingestion. Synchronizing them with the downstream tools is a challenge. So any delay in analyzing this data can directly affect traffic management, predictive maintenance, and ultimately driver safety. Plus data spikes can happen unpredictably. So we need a flexible infrastructure to handle it all the times. Many organizations bring, they bridge Kafka with data lakehouse solutions using connectors like Kafka Connect, Pulsar IO, or custom scripts. But there is a big challenge here. The challenge here is that let's say you have a Kafka cluster and then you have a Iceberg. So you have now 2 separate schemas. And if there is a data movement between those 2 schemas and then you have an error handling, how will it poses an operational challenges around that. And let's say you have 1,000 topics in a Kafka cluster, and you have how do you want to map those topics to a particular number of tables in the Iceberg. So there could be a cost here associated with it, because different number of connectors that you are spinning up. And so that's like a high operational overhead, and the ETL pipelines are very brittle here because it adds the latency. So kind of similar to what I spoke. So you have the different apps talking to the different brokers on the Kafka, and then on the connector side, you're talking to like Databricks or Snowflake, a traditional ETL pipeline, right? But they are the 5 costs associated with that pipeline that I mentioned there. One of them is the interzone data transfer. Second is the expensive disk-based replication. third being over provision compute. Fourth is connector overheads and the duplicate data copies. I'll break down each further. So in the first one, where the high availability is essential, we know that most Kafka users deploy across multiple zones, but there's a catch. Every time an application sends data, Kafka replicates it between zones, and apps clients need to send data to Kafka across multiple zones, leading to additional networking costs. Now, the Kafka ensures durability by storing 3 copies of data across zones. That's great for reliability, but you're paying for those replicas both in storage costs and interzone data transfer. And in Kafka, both compute and storage are tightly coupled. If you need more storage, you have to scale compute as well, whether you need extra processing power or not. Now, moving data from Kafka to cloud storage requires connectors. These connectors need extra compute resources, and they are network costs each time data flows through them. And if you're leveraging multiple analytical systems, you end up storing the same copy of data multiple times, once in Kafka, then again in every analytics platform. That's an exponential increase in storage costs. With that, I will pass the mic to CJ Go from Stream Native to discuss Ursa, how this is going to handle the challenges that we talked about so far.
Thank you, Gaurav. I think everyone here is coming to Databricks Summit is all about Lakehouse. So there's obviously there's an increasing interest about building an open lakehouse, and there's an open standard has been arising. Like Iceberg is probably the most common one. Delta is another popular one. So those are kind of the open table formats, and you can build your future-proof lakehouse ecosystem based on that. And both systems have been kind of running at very large scale. It can support continuous ingestion, very like ideal shoot for the kind of the streaming data, massive streaming data needs that Gaurav just mentioned about. I mean, automotive industry is one of the example, but there are so many different industries like security, like observability. I think a lot of these streaming data need to kind of get into kind of lakehouse for much cheaper storage options and for analytics purpose there. And also both of the system, there's another kind of increasing topics on the data catalog side is the entire open lakehouse architecture, including a really strong governance features to ensure this high data quality and compliance. So with all this coming all together is kind of we have to kind of looking back into the entire pipeline. While we have a really good foundation on the lakehouse side, how we can solve the entire data ingestion all the way from your data source through Kafka, through connectors into Lakehouse, and solve some of the challenges that Gaurav just mentioned about the limitation or cost drivers of the entire pipeline. And that's what we kind of have been kind of working with quite a lot of industries like work and also Fortune 500 companies, including Gaurav's company, on solving some of the challenges that we are seeing is we're building a Kafka-compatible Lakehouse native data streaming engine. So a simple idea to kind of explain that is eventually, since your data destination is Lakehouse, and we probably don't need an additional system to just store one copy in on a local disk and then move the data outside of the disk and then put into Iceberg. So if we already using object storage as the storage medium, we can probably just build the entire system based on that. So we follow some of the principle that the entire Lakehouse ecosystem have been doing on data lake and warehouse side is to decompose the entire system into modules. So the way how we decompose it is into looking into the data storage side is, can we introduce streaming extension to the open lakehouse format? So in that way, it can accept some of these streaming requirements like a PAN faster pen and be able to kind of replay the entire uh, semantic based on the streaming requirements there. And then we have the broker layer, which became the more or less a routing layer. So you can receive the data, batch the data, and then write the data into the to the data storage side. Then you have the metadata side to managing all the streaming semantic, mostly are kind of the offset requirements, because in order to supporting Kafka compatible protocol, you need to have some of the concept is called offset. So maintaining some of the offset in the metadata side, maybe those metadata can pushing towards more the catalog side. So it could be part of the concept of catalog. So in that way, we kind of formalize the kind of three layers. One is the data storage layer. That is a kind of augmentation over the existing Lakehouse. The broker layer became stateless, so it would just focus on routing and some of the quota control to making sure you're managing the entire traffic. And on top of the broker, you can support different protocols there, so that we uh, uh, support both kind of two popular protocol there. One is the Kafka, the other one is Pulsar. For people who doesn't know about Pulsar, essentially is kind of unify messaging and streaming protocol. So it allows you not just using it as a streaming system, but also as a messaging queue, which is flexible for some of the end user facing business application. So to put all these together, it's Kafka API compatible, but to a certain extent is more multi-protocol, protocol flexible, because you can plug into different protocol. Because the data is being pushing towards more using object storage as the storage medium, you don't store data within a broker, so broker became stateless. And more important, it's actually leaderless, is because it doesn't have the concept of leader that need to replicate across different disks. It's because everything just go to object storage. The storage there is Lakehouse native, because all the data, once it's getting in, it's actually landed directly as an Iceberg table or Delta table. It have a really nice, simple way to integrate with catalog, to making sure all your streaming data is actually being governed by the same catalog there. So I think if you have kind of following data streaming ecosystem, you probably already hear some of the kind of a trend that in the data streaming ecosystem is about topic to Iceberg integration, and that including some of the vendors in the data streaming space. Like Confluent had a concept of table flow. So you get a Kafka topic, you can turn on table flow and writing to Iceberg table or Delta Lake table. In Red Panda also have a similar concept called Iceberg topic. Essentially is you write a copy to Red Panda, and Red Panda can persist the data again into Iceberg table, but really kind of peel the onion to kind of see what's behind these integrations there. It's essentially is a connector running aside, not either inside the broker or outside the broker. For example, Confluent Tableflow is using Flink, is reading from a Kafka topic and writing to Iceberg. And Red Panda is essentially implementing some sort of connector logic as part of broker to reading reading the data from the Red Panda topic and write to Iceberg. So it's not really kind of a clean topic to Iceberg integration. And the way how we did is quite different from those approaches there, because if we feel we have to kind of using some sort of connectors, then we can use the original pipeline that Gaurav just showed, is just putting up some of the connectors. It doesn't need to kind of move some of the complexity within the broker itself. So we kind of step back looking into what exactly needed from a storage layer perspective. So this is a diagram, a very kind of simple diagram to visualize the needs of a data streaming system like Kafka, like data streaming system. So all the concept is very simple. It's a data stream. Sometimes it's called a log topic partition. You have a sequence of records, you append to a log, you get an offset, you're able to kind of retrieve the record from the offset. From implementation perspective, it essentially break down the log into multiple segments, and you have some sort of offset index to reference where I can fetch the record based on the index. So that is a very simple abstraction. And if you take a look at how it was implemented within Kafka, it's very simple. Is both your data and your index are local to the broker, and you have many brokers. The data, both the segments in index are kind of replicate across different brokers there. So that is a very simple disk-based Kafka broker. And if you introduce the concept of tier storage, the concept is still similar. It's just like you moving some of the segments from local disk to remote, and then you update some of the index to reference the segments in the object storage. So the entire concept is still segment and index. And there's another system called Pulsar. Pulsar essentially is doing things quite differently. It doesn't directly store all the segments of a given partition within the same node. It's actually break down the entire segments into different storage nodes there, but moving the entire kind of offset index towards the metadata storage side. So you can have kind of two layers. One layer is the entire offset index is moving towards the metadata storage, and you have the segments is break down into the storage there. But the segments doesn't tie to a given broker. It's actually the segments is distributed across different storage nodes, which is called Bookie. I'm not going to details on the Pulsar side, but I just want to kind of visualize how does the entire data streaming storage evolve. And if you're putting the tier storage concept into the picture, it's also very simple. It's just some of the segments that has been stored in disk, we can simply just moving into object storage and update the index in the metadata side. So that's kind of how the current data streaming system work, but they operate on both kind of two concepts. One is the segment. In Open Lakehouse is actually a set of data files, is a set of packet files there. And the other concept is actually offset index. And in Lakehouse format, you will see in Delta is a Delta log. And Iceberg, you have the manifest file. It's also kind of sort of index that is reference what the data files has been used by this Lakehouse table. And you can see in data streaming is very similar. It's just a bunch of the segments you can view as a bunch of different files there. And then you have an offset acting as a metadata index to reference those segments. So we kind of looking into how the entire streaming formats kind of evolve, and looking into how Lakehouse kind of evolve. We find there's some common similarity between these two systems. There is in the Lakehouse side you have a bunch of the packet files, and then you have the Lakehouse metadata that is reference those packet files. And in the streaming side, it's the same thing. You have a bunch of the segment files, and you have the offset index. So we're kind of moving in a way is, can we just leverage the same concept in the Lakehouse side? Is if we append the data in to the right-hand log for this given stream, which it has its own index, which is the offset index. But over time, we can leverage some of the compaction work to compact the row-based streaming data into column-based like packet file, and then building the metadata around these packet files. And that's kind of the entire concept of Ursa Stream. Essentially is an augmentation layer over the existing Lakehouse table. So if you see in the right side of the screen it's entire like the packet files and Lakehouse metadata there. We're just adding these real-time streaming data as an extension or augmentation over the Lakehouse tables there. So that's kind of the entire philosophy we build like Ursa as the storage there for streaming. And To give you some more concrete ideas, there is for a given stream, when you start kind of appending the data, let's say you have a Kafka producer sending to a broker, broker append the records into a given partition, and that is how it would look like. It basically breaks down into different what we call write-ahead log objects. Write-ahead log objects, you can think about, it's a row-based format, so we just append different rows into the file. The role can be interpreted based on the Kafka schema, the schema information coming from the Kafka topic, which can be an Avro, JSON, protobuf. And so write-ahead log object is kind of a low-based data file of low-based segments there, and you keep append. And then there's a background compaction work. Essentially what it does is it will just take the write-ahead log objects and doing the compaction. And the compaction here is not a Lakehouse table compaction. It's more like the streaming compaction. Is it take the write-ahead log objects and leverage the information coming from a schema registry and convert the row-based, each record from given Kafka schema into Parquet schema, and then rewrite some of the write-ahead log object into Parquet. So in that way, you can see over the time, it will become a mix between Parquet files and write-ahead log objects there. So Parquet file essentially is the ready to use like a columnar data, which can be used as a Lakehouse table, and write-ahead log is still kind of the latest streaming data, which can be used for streaming requirements there. But if you want to replay the entire stream, you can still kind of seek to the earliest offset and read the data from the columnar format. But because the entire Kafka protocol right now is still kind of a row-based protocol, so you still need to read the entire columns and then convert the column data back into row format, which could be Avro, JSON, depending on the schema information in the schema registry. But that conversion can be done in the broker layer on forming that kind of structure for realizing the Kafka schema, which kind of, it would burn a little bit more CPU, but you are saving tons of the network traffic, IO traffic, reading the historical data from the object storage. So that's kind of the last step. It's just like repeated this again, is you keep compacting those write-ahead log object and merging into these large Parquet files. It's very similar to like table compaction for maintenance, but it's more applying for the streaming world there. So to put all these kind of together, essentially is with Ursa, you have kind of extension over the existing Lakehouse format with write-ahead log objects, which is more for streaming. And then we can integrate with external catalog for register those Parquet objects as a table information into the catalog. So those data can be immediately discovered by catalog services that can be used by the downstream applications there. And one thing to call out is in the streaming semantic, you can think about it's more like a append-only table. So you really append everything into a stream. So the table being presented by the produced by the compaction essentially is a kind of append-only table. We call it an internal table. So it's an internal table to the stream. But sometimes you probably don't want to keep all the historical data. You want to do upsert. We are using the same mechanism is during compaction of the write-ahead log objects. We actually do upsert and produce more compacted Parquet files, and then write to external object storage we call external table, because those are the data that is really be compacted by upsert. It's actually not streaming data anymore. It's produced more like a more compact structure for a table. So we support both modes. Is like append-only table. You can use it as a kind of upsert table. It's just using the, for example, you're reading CDC from Kafka using Kafka protocol, and then once those CDC change streams in landing into a Kafka topic, you can use these external table modes to really compact the data based on the certain keys there, and then it will produce more like a compacted table structures in the Iceberg side. So that's the kind of the entire concept of the Ursa storage. But if you really putting all these together, you'll find the way how we design the Ursa is actually an augmentation over existing Lakehouse tables there. So Lakehouse, you have the metadata, which either is Delta and data log in the Delta table, or a manifest snapshot in the Iceberg table, and underneath is all the Parquet files there. And I know Iceberg v3 essentially is pushing the consolidation or unification of the Iceberg and Delta. So you see some of the underlying data type is also consolidated in the data file side. And I think there are more changes is going to happen within the Delta Lake and Iceberg side to making sure the metadata is also interoperable between formats there. But those kind of formats is still focused on more Lakehouse concept. It's a table-centric concept there. And what we're adding here is to kind of adding additional role-based formats into the Lakehouse system, and adding additional offset index to the metadata side. So in that way, it's actually being can be used as a kind of a Kafka-like data streaming capability there. So it's more like an augmentation rather than a replacement over the existing Lakehouse. And to put all this together in kind of a reality on helping Fortune 500 companies implementing this, essentially you can think about Ursa essentially bring in additional metadata plus Kafka-compatible brokers. So that will sit on top of your existing Lakehouse, and those could be served as the ingestion there, so you can get data through existing Kafka protocol, and those data can land into Iceberg side. And those data can be used for your streaming application. Your existing Flink job, Spark streaming, structured streaming job can continue to work there. And there will be kind of a conversion of kind of compaction that is happening between the streaming layer and the Lakehouse there to produce different type of kind of what we call data products there. So to really putting this into the kind of reality is now you will become having the same set of the data, same copy of the data, and that data can be served as a Kafka topic. So in that way, you can produce through Kafka topic and consume through Kafka topics there. But the same copy of data is actually being materialized or being viewed as an Iceberg table. So your downstream query engines can query those Iceberg table or Delta table there. And so this would become just one data product, one same copy of the data, and being consumed either as a stream or as a table. And then putting back into the first slides, in your current Lakehouse system, it will become kind of unified data products. Each of them can be either used as a stream or as a kind of a table there. So this, I think a lot of people will kind of be curious is that you already have a Kafka system, you already have a Lakehouse, and a lot of people probably already setting up some of the pipeline using connectors. And if you want to kind of use Ursa, what is the kind of a simple way? We do have a kind of migration tool called universal linking, but it's very similar to the concept of Meter Maker, but it's done entirely different. Meter Maker is a broker-to-broker replication, so everything is going through network, which is very expensive. So if you want to move from one of the existing Kafka deployment to another deployment, you're probably going through network hops multiple times there. And since the entire system we're building is based on Lakehouse is running on object storage, so the entire replication here is we are using object storage as the replication layer. So the way how it does is you already have a cluster. You can create a link, and the link itself essentially is just reading your Kafka data and writing into object storage. And when you're writing into object storage, because it's going through the Ursa format, it can actually materialize your Kafka data directly as an Iceberg table. So for the first step, it doesn't go through the network. If you want to move from an existing Kafka deployment, you're actually moving the data into object storage, and which give you a very nice property here is that if you want to examine if your data is actually being kind of fully replicated, you can just looking into the Iceberg table and then figure out what exactly has been replicated. And if you don't want to migrate, you can still using Ursa as a way to build your real-time lakehouse there. It can be acting as a tool to just reading your existing Kafka topic and writing to object storage, and eventually making your Kafka topic available as an Iceberg tables there. And then the last step is not the least important step is when you feel comfortable, okay, the data is entirely replicated in object storage. If you want to start consuming using the Ursa brokers there, you can then spinning up a broker and then start consuming the data in the Lakehouse side. But the first two is the most important one, is actually using the object storage for replication, save your costs, and be able to kind of rolling out the entire system based on your own path. I think that's kind of all the information we want to kind of share. The idea here is right now we kind of we see a lot of consolidation that is happening in the Lakehouse side, and data streaming has been treated as a silo to a certain extent. While a lot of conversation, I attend some of the open Lakehouse mini summit yesterday. A lot of discussion is how to make Iceberg much faster so that you can ingest data within minutes, kind of pushing towards seconds, and which has been kind of done by the data streaming ecosystem through Kafka, through Pulsar, through many different of the messaging and streaming system. And we see these two ecosystem is actually start kind of converge through some of the open standards there. So we hope the Ursa approach that we are taking here, it could be some extension that can be added to Iceberg or Delta Lake, can become the real-time extension or real-time part of the Iceberg spec. So hopefully that will simplify people building a real-time streaming lakehouse there. But until that point, I think the experience that we're sharing here could be used as a reference for people looking into building their own real-time lakehouses system. And we have some bunch of the resources there to help people to learn a bit more. We also have some of the blog posts and podcasts if you want to learn about this subject more. And I think that would be all the kind of presentation from Graf and me. And now it's ready for Q&A.
Thanks so much for the presentation. So when storing data into the Delta format, are you dealing with small parquet files issues, considering that these are small segments coming from the stream, how you're handling the performance in the Delta?
I think the question is about how we dealing with the small files there. So there's kind of two parts. If we are looking into more like an internal table, which is managing by the streaming system there, we have the stream compaction. When we do the compaction, when we're converting the write head object into Packet files, we're taking that file size into consideration. And over time, we also merge some of the smaller Packet files into large Packet files there. We have a mode called external table. External table here is more like we upsert into an external table. External table could be like Databricks a table managed by Databricks Unity Catalog, could be a table managed by AWS S3 tables. So in that way, those Iceberg or Delta vendors were kind of managing the table maintenance for that given tables there. So
thank you. One more question. So in terms of replayability of the stored data, right? So we are storing those segments in the table. Can we replay the stream from these tables?
Yes, we. I think the question is if we can read the entire history through streaming for the entire tables, right?
After the stream is stored in the table, can we read the data from the tables as a stream?
Yes. Can we read the table as a streams there? We can. Is because in the metadata side we will manage the additional metadata called offset index. So that offset index essentially give us the ability to formalize a table as a stream. So in that way, all the nice properties that you see in Kafka streaming, you can get from there because it has an offset being associated there. And maybe a little bit more deeper into the streaming offset, essentially it doesn't store each index for each record, but it's reference each packet file, and packet file would also have its own what's called record count. So essentially is within packet file we can use the record count and plus the offset index towards the packet file. We can use this to compute calculation where we can get to read the records there. So all the nice properties you can get from Kafka would just remain the same.
Hey, thanks for the talk today. Question about what type of latency and availability are you assuming, given that we're kind of going all in on Iceberg to read and whatnot? What type of latency are you seeing for consumption?
Yes. Consumption should be really fast. It's because especially if you're telling reads, because you have a broker, your broker would actually have a cache or buffer. So if you're telling read the entire stream, it's actually buffer in the broker side, so there's no latency kind of delay. But you do see a write latency increase because we are using object storage as the storage medium. Right. So a typical S3 object writes you will be seeing in a range between 200 milliseconds to 500 milliseconds.
Okay.
So your write latency will see a bit higher. But if you're using S3 Express as the write-head log, you would probably be lower the latency towards in the range between 20 to 50 milliseconds there. But obviously, S3 Express Zone 1 is much expensive than S3. But the nice property here is essentially is you can use S3 Express Zone 1 as the write-head log objects there. And then over time, the data will be compacted into the standard S3. So you can still using the standard S3 for the entire historical data and use S3 Express Zone 1 from the write-head log, which you can lower the entire latency as well.
So we're thinking like tens of milliseconds when fully optimized. So like if we're thinking about fraud or marketing use cases where I really need kind of that real-time data or near real-time, it would be suitable, or would you recommend a kind of a latency-specific model for that?
That's a really good one. We designed the system in a good way. Is the write-head log object can be actually disk-based.
Yeah.
So in that way, you can think about that disk being acting as a cache or fast write, and then you can lower if you're using disk, you can lower the entire latency into within 10 milliseconds. But S3 Express Zone 1, you can only get closer to 20 milliseconds. But I think with over time, I think AWS is probably going to lower that within 10 milliseconds. once that get there, you probably just entirely using AWS S3 as the solution. I think we are running out of time, and I'm happy to connect like Graph and me in the hallway there. Thank you.